Welcome to AI Machine Learning Workshop, the tutorial before your tutorial, Part 7, brought to you by Blackmagic AI. So if you want to know more about us, go to our website at blackmagicai.com. You can like us on Facebook, subscribe to this YouTube channel, and sign up on our email list. Recall that this tutorial series is divided into Part A, where we cover the theory and concepts in AI and machine learning, and Part B, where we apply theory, concepts, and tools from Part A to actual coding example projects. So this video will continue our introduction to neural networks and explore the details of the exclusive OR neural network we introduced in Part 6 video. And in this video, we will learn how to use backpropagation to find the weights and bias values needed to train our neural network. As a recap of the Part 6 video, we showed how a single perceptron can approximate the AND logic function given the correct values for its weight and bias values. We also showed how to apply an activation function to the perceptron output to customize the positive and negative real values into the desired binary values of 0 and 1. We demonstrated how a single perceptron was unable to approximate the exclusive OR logic function, but we suggested that if we combine multiple perceptrons into a multi-layer network with nonlinear activation functions, it will be able to approximate the exclusive OR logic function. We call this network of perceptrons a neural network and explain how we must use a more formal method to calculate the weights and bias values for the neural network. We briefly introduced the concept of backpropagation as a way of obtaining the weight and bias values for our network, but we will explain the algorithm in more detail in this tutorial video. So the goal of this tutorial is to explain how we can find the weights that allow our neural network to give the correct outputs. We will explain how the backpropagation algorithm is used to do this, and we will start with the Perceptron training rule and develop each step in an evolutionary process as we develop the rules for the backpropagation algorithm. The road to backpropagation starts with learning about the Perceptron training rule, which will give us the background we need to understand the delta rule, and then we'll talk about gradient descent and backpropagation. So the Perceptron training rule will give us the general background we need to understand how the weights in a neural network are updated to train it. In the delta rule, we will explain a mathematical expression that allows us to calculate these weight updates. Then we'll talk about gradient descent, which uses the delta rule to help calculate the weight updates. And then we'll explain how we can use the delta rule with gradient descent and the backpropagation algorithm to find the weights and bias values in complex multi-layer neural networks. This diagram represents our exclusive OR solution using a neural network. But as you can see, it has many weight values in there. But how do we find the weights so that our neural network gives the correct output? This is an outline of some of the topics we will cover in this tutorial. Loss and error function, gradient descent, backpropagation, overfitting, convergence, and hyperparameters. We'll touch more of those when we get into our actually coding example project. But in the previous tutorial example, we found that a single perceptron can approximate the AND logic function given the correct weight and bias values. Now in that example, the weight and bias values were provided to us, but we'll take a more in-depth look in this tutorial on how to obtain these values. First, we will try to get a conceptual understanding of how to obtain these values, and then we'll show the mathematical representation of the concepts, but we will avoid diving too deep into the mathematics because the purpose of the mathematics is to program a computer to do the computations. But in this tutorial, we will be using the TensorFlow framework, which handles that for us. So all we need is a conceptual understanding to know how to apply the tools correctly. You can seek out more in-depth tutorials for understanding of the mathematics after you grasp the concepts in this tutorial. So just a recap of how our neural network works. So you can see here we have our input layer passes the inputs to the corresponding perceptrons 3 and 4 in the hidden layer. No calculations are done by the input layer. Its sole job is to forward the inputs to the corresponding perceptrons in the hidden layers. Now each input is multiplied by a corresponding weight, and it's applied to all the perceptrons in the next hidden layer. And the x sub 1 input is multiplied by a weight that goes from 1 to 3 for input 3. And then it also is multiplied by a weight from 1 to 4 before it is applied to the number 4 perceptron. And the same thing for input 2. The outputs of the hidden layer are multiplied by their corresponding weights also, and are fed as inputs into the perceptron of the output layer, which gives us our final output y5 sub 5. The output layer produces the y output as our final result. And recall that our neural network model learns relationships between inputs to the correct outputs from the data set we present to it. The key ability of a neural network is that it is capable of approximating any function once trained on a data set. The features in our data set are the properties we have identified as important to producing the correct output. And recall that weights amplify or dampen inputs depending on how much the features contribute to the correct output. Let's conceptually derive how we can determine the correct weight and bias values. So let's come up with a Perceptron training rule that's a simple way to determine the weights. To start, we will assume some random values for the weights and bias. Then we will apply our first set of inputs from our data set. Our first set of inputs comes in through this features and goes into our model, which is our familiar Perceptron diagram. We are using supervised learning here, so we already know what the expected output should be, and that's the label input you see here. So we have our features from our data set coming into our model, going through our inputs, our summation, our activation function to get a final output y, so that we call that an inference or a prediction. And then we have our label, which is what our expected output should be, which we have because we're using supervised learning approach. So the difference between our initial output based on our initial guess of weight and bias values, y out, and the expected output is called the error or loss, and also called a cost. You can see by making small adjustments to the weights, we can reduce the difference between the actual and desired inputs. So if we adjust these weights by some amount, that will change our y out, and by changing y out, we can change what the error is. And remember, the smaller the error, the closer our model is to giving accurate output predictions or results. So if we have a large error, you can see we need to increase y out by increasing the weight and bias values that amplify features that are important to reduce the error. If we have a negative input coming from our x sub 1, we would want to dampen that with a smaller weight value. So that smaller weight value means a smaller negative number in our summation, so that means less is being subtracted, so that means our y out will turn out to be bigger. And a bigger y out means we are going to have a smaller e. So a negative error means that the actual output is larger than the expected input. So you can see here, if y out is bigger than y expected, then e is going to be negative. That means that the weight should be reduced for positive inputs and increased for negative inputs for the reasons we mentioned before. A positive error means that the actual output is smaller than the expected output, and the weight should increase for positive inputs and decrease for negative inputs. So that brings us to our concept 1, the Perceptron training rule. What we just described is that we're going to make small adjustments to these weights. That's called a weight correction, represented by this symbol delta W sub I, where I represents the particular weight of interest. We're going to add that to our initial guess of weight value, and then we're going to get a new value. Now hopefully that new value will contribute to making E smaller. So the next question is, how do we calculate the weight correction? What is it dependent on? So that brings us to concept 2. So our weight correction, as we mentioned, is proportional to the error. So if we have a very large error, it makes sense that we should make a bigger weight correction. And also it's dependent on the input, x sub I. So again, the magnitude or size of the input and its sign also determines how much of a weight adjustment we should make. And then here we also have introduced another parameter called the learning rate, represented by this little alpha symbol. So learning rate is a small value between 0 and 1 that we multiply to tell us how much of that weight adjustment to make. And then the negative sign is subtracting a weight. So that negative sign will change depending on the value sign of E and X. And based on our previous discussion, we showed how the negative values can increase or decrease that weight in order to decrease the error. And once again, we have E expected minus E out is our error or loss. Now remember, the point of machine learning is for the computer to learn the relationships between the inputs and outputs, which means we need a way for it to learn the weight and bias values on its own. The Perceptron training rule we learned in our previous discussion is great for learning the weights for linearly separable problems such as the AND example in our previous tutorial, but it is not guaranteed to find the weights for nonlinear problems like we discussed with our exclusive OR function. That Perceptron training rule is not guaranteed to converge. So that's why we're going to continue on with more discussions on how to train our neural network, because the rule we presented previously only applies to that limited scenario, but it's still a basis for training the more complex neural network. If we had a mathematical expression or function for the relationship between the error and each weight, which is this purple curve here, so you can see as the error gets smaller, it reaches some minimum, and at that minimum we have a blue horizontal line, and that point where that line touches the bottom of the curve, that's the weight that gives the minimum error. So if we had a mathematical expression for this purple curve, we can use it to find the minimum error point, which is this on the y-axis, which is also the point that tells us the weight value that gives the minimum error. So remember, from our previous discussion, this is what we had in error, in which we took one sample, we took the expected and subtracted the out. So a common statistical function used to calculate the error in a data set is the mean squared error, represented here, MSE, also known as the cost function. The main difference between the error we calculate in the Perceptron training rule and the mean squared error is that the mean squared error calculates the error for the whole data set. For example, we calculate the error for each row or data sample in our AND and exclusive OR truth table for a combined aggregate error for the data set. So more specifically, the mean squared error gives us kind of an average of the errors or square of the errors for a set of data points and not just for one point of the data like we had previously. So this mean squared error is over all samples in our data set. Now, if you look at our mean squared error, you see that nowhere does it show any relationship with the weight values, but that's what we need. We need this purple curve, something that gives us the error and the relationship with the weights in our network. How do we derive an expression for the mean squared error and the weights? But instead of subtracting a particular value from the actual output, we replace it with the Perceptron's output function, which is here. So recall, this is the mathematical representation of our Perceptron. If we substitute this expression in for y out, we get a mean squared error or cost function that has the mean squared error on one side, and then the other side it shows the relationship with weights. This gives us a complete mathematical function containing the relationship between the error in our data set and the weights. Now the purple curve in our diagram only shows a one-dimensional input using one weight in a 2D plane. But our AND and exclusive OR examples are two-dimensional because they have two inputs and can be represented by a plane curve. So as the number of inputs increases, so do the number of dimensions to our error function. Beyond two inputs, it becomes difficult to visually represent the error function, but the concepts and principles remain the same and apply to any number of input dimensions you will encounter. We now have a mathematical expression for the relationship between the total output error and the weights in our neural network, or this purple curve is represented here by our error or cost function. So that's this purple curve. We need to know how to calculate this blue tangent line to the error function curve. We can see from this diagram that the line is horizontal at the minimum error point, which also corresponds to weight values which give the neural network output closest to the desired output. If the blue line is sloped to the right, it tells us we need to move the line in the negative direction to get it horizontal, as represented by the orange arrow here pointing the direction we must go. If this one's sloping to the right, we slide it down to get it more horizontal. Now, if the blue line is sloped to the left, it tells us we need to move in a positive direction to get it horizontal. So in summary, we need a mathematical expression that tells us the direction to move along the purple curve to make the blue line horizontal. And then we will find the minimum point on the error curve that gives the smallest error for a specific weight. So the error gradient is the mathematical expression that we can use to determine the direction we need to move along the curve to find the minimum point. So the error gradient is that tangent blue line. So once we have that, it'll tell us what direction we need to move in order to get to that minimum error point. The gradient can be obtained by applying the operation represented here by this symbol to the error function, which is represented here, which we discussed previously. So once this operation is applied to our error function, the tangent blue line direction or slope is represented by this symbol, which is the error gradient. When you see this symbol with the E total and the W sub I, that means we have taken this error cost function with the relationship with the weights in it, and we have a way now of calculating this tangent blue line. So like we showed previously, if we know the slope of this tangent blue line, that tells us the direction. So that's what this new symbol gives us. So when you see this symbol, just think it's going to give us the blue line tangent to our curve, which will tell us like which direction we need to move. Like we said, left or right. So we need to move in a negative direction or positive direction. This error gradient, it represents the rate of change of the error with respect to the weights. So we have the error with respect to the weights. So a small rate of change means that our tangent blue line is close to horizontal. Remember, our AND and exclusive OR models have multiple inputs, so they will be more likely represented by a surface plot like this. And once again, as we get in higher dimensions, the surface plot becomes more complicated. So as we go into higher input dimensions, our plot becomes a higher dimensional surface that is very difficult to visualize. Now recall that our original goal, is to find the weights that allow our neural network to learn the correct outputs. The delta rule is a mathematical expression to calculate the neural network weight updates needed to train our neural network, similar to our Perceptron training rule. Because we have to make small adjustments in the weight, and we can reduce our error to get the correct outputs. The curve in this diagram illustrates how the lowest point on the curve is the point with the smallest error that occurs at a particular weight value. So this green dot, that's the smallest, lowest error, and it occurs with this weight. Now keep in mind this diagram only shows one weight, which is not very practical or realistic, but it is a simplification to help in our understanding. The actual plot will look more like the surface plot shown previously, but most practical applications will be more complex and have multidimensional surfaces due to the multiple weights in the neural network. Now, the delta rule tells us the amount the weight should be adjusted to converge towards a minimum neural network output error. It does not directly give us the minimum error point, but it can be used to help determine the minimum error point shown by the horizontal line at the bottom of the curve. We will use the delta rule expression to find the minimum error using a technique known as gradient descent. So gradient descent works like this. So we pick the starting point, we create this line tangent to that point, which is our error gradient, and then the negative direction of the line, or the part pointing towards the minimum point, tells us the direction to travel to find the minimum point. So it's sloping down, and like we said previously, sloping down means we have to go towards the right, or a more positive direction for a negative sloping tangent or gradient. Now we take a small step in that direction, represented by alpha, our learning rate. So remember we mentioned that before, that's a small constant between 0 and 1. So we take a small step in the negative direction, and then we create another tangent line at that new point. This movement from our previous point to the new one tells us how much of the weight correction we need to reduce the error. So you can see we started off with initial weight, we moved towards the reduced error point, that gives us a new point. So the distance we traveled, that's our weight correction. So remember, our delta W is our weight correction. We add that to the original and we get our new weight value. And you can see our new weight value, Wi plus 1, is closer to the actual weight we need to get the minimum error. Now we will repeat this process until the error is within acceptable levels. So concept 4 is the delta rule. So that was this purple line. So we can calculate that little weight correction by using the learning rate, which tells us how far in that direction to travel. So you can see if we made our learning rate too big, it might overshoot that minimum point. If we made it too small, it could take forever to reach that. So we have to find a compromise, the correct learning rate that gives us the best results. So we have the alpha times our gradient, and that gives us this little delta W. So you can see that here. We have our direction to go, then we step forward in that little direction by alpha, and that gives us our new point, which is our weight correction. Now what is the learning rule? Well, in concept 5, the learning rule is similar to what we had for the Perceptron training rule. So we'll just take the learning rule as we take our initial weight and we adjust it by this weight correction, which is now calculated using the gradient and the learning rate. Now this process is called gradient descent because our gradient is descending towards the low minimum point. So if we had started our initial point right here on the right hand side, it would be the same thing, except we'd still be going towards we'd be going in a more negative direction if we started over here. So our initial guess where we pick could be anywhere on this purple curve, but because we have this gradient telling us the direction to go in, we'll always kind of go towards this minimum point. And once again, this is an iterative process, so we'll just keep repeating that till we get as close as we can to our actual weight value. Now we may not get exactly there, but we'll get close, as long as we're in acceptable levels for our model. All right, so just to recap, the delta rule, so to recap, the learning rule to get our weight corrections is to take our initial weight that we guessed, and then we subtract our alpha times our gradient. So that's a step in the direction of a lower error, and the way we calculate that weight correction is the delta rule. So we need the delta rule that applies to our learning rule, but we need gradient descent, which is this iterative process of moving along this curve until we get closer and closer to the minimum error point. This diagram is our neural network, our simple neural network that we've been working with. So we can use the delta rule with gradient descent to find the weights that give us the minimum error and thus the proper weights for a trained neural network. So once we get those minimum errors and those weights, our network is properly trained. So you can see we have multiple weights here. We have weights from the hidden layer to the output layer, and we have weights from the input layer to the hidden layer. Now we need to calculate the error gradients for all the weights in our neural network. But how do we do that when we only know the error for the output? The hidden layer does not directly have access to this error. So you can see the weights 3, 5, and 4, 5, they are embodied in this symbol. So the hidden layer does not directly have access to the output layer error. Now we have to introduce backpropagation, which allows us to transmit or propagate the output layer errors back to the hidden layers so that we can calculate error gradients and apply the delta rule with these gradient descent to adjust the weights in the deeper hidden layers. And we'll get the minimum error at the output layer. We start the expression for the gradient, which allows us to calculate the weight sub I for the minimum mean squared error that's here. Now when I is 4, 5, or this weight here, the expression becomes this symbol. So this says we have the relationship for the mean squared error or gradient and this weight. So remember our curve, our purple curve. So we have a purple curve for this weight. Now the adjustment for W sub 4, 5 can be obtained by calculating this gradient. So we know how to do that. But now we need to calculate the gradient for weight 2 to 4. But as mentioned previously, we don't have access this 4 point to the total error and output of neuron 4. Now we need to calculate the gradient for the weight from 2 to 4. So as mentioned previously, we do not have access to E total in this hidden layer to calculate the gradient, but we can calculate the gradient for E total and output of neuron 4. So we can get E total and out 4 because we can calculate that relationship. Then we can calculate the gradient for output of 4 here and input into 4. So we can get that gradient. So see how we skipped over? Now we're here in this deeper hidden layer. And by continuing this process of chaining gradients together, so for example, now we have the gradient between the input of 4 and the weight from 2 to 4. So now we've finally reached this weight in the hidden layer. So you can see how we chain together all these different gradients that we can calculate to propagate this E total back to our weight 2, 4 in the hidden layer. Now, once we have all the gradients, we can iteratively apply gradient descent algorithm to find the weight adjustments that give the minimum total output error. And we continue to iterate until our neural network converges, which means that further iterations no longer significantly improve the total error. That's our road to backpropagation. So let's recap the backpropagation algorithm to train neural networks. How does it work? Well, we initialize our weight with random values. We can set our bias equal to 1. We activate our neural network, which means we get an output from our neural network. And then we calculate our error gradients. And we can use backpropagation. And then we update our weights using the delta rule as we go backward through the network. And we iterate until our mean squared error converges. That just means further iterations no longer significantly change our output. At that point, we want to stop the iterations. That concludes part 7 of AI Machine Learning Workshop, the tutorial before your tutorial with an introduction to neural networks. Go to blackmagicai.com, like us on Facebook, sign up on our email list, and subscribe to this YouTube channel, and you will be notified when additional videos in this series are posted. Thank you for watching.